Hello students, in this video we'll discuss the Parseval relationship using the Fejer means. Recall, the Fejer kernel has the following form. It's Kn of x, and it's the sum, j less than or equal to n, 1 minus absolute value j, n plus 1, e to the I, jx. In the previous video, we found an exact formula for this. It's 1 over n plus 1, the sine of n plus 1 over 2x squared over the sine squared of x over 2. Okay? Now let's make some remarks about the Fejer kernel. So here's the first property that we know about this Fejer kernel. The first property we know of it is that since this is the sum of Dirichlet kernels, so since k is 1 over n plus 1 d0 of x all the way down to dn of x. If I integrate, this implies 1 over 2 pi, the integral from negative pi to pi of kn of x dx. Well, each of these Dirichlet kernels integrates to 1. So this is going to be an 1 over n plus 1, and then a 1, 1, 1, 1, 1, 1. All the Dirichlet kernels integrate to 1. And so I have n plus 1 over n, so the Fejer kernel integrates to 1. That's the first condition we need for an approximation to the identity. Okay, the second condition we know is that since kn of x is greater than or equal to 0, because of this representation over here, we know that the integral from negative pi to pi, 1 over 2 pi, the absolute value of k of x dx, I can remove the absolute value because it's not negative, right? So this is just going to be equal to 1, so therefore this is equal to 1, so in other words, this is bounded. These numbers are bounded. Okay, the L1 norms are bounded. In other words, I can sort of write it like this. I can say that the L1 norms of this family Kn are less than or equal to a constant c. In fact, that constant c is just 1, right? And the final condition is this. I would like to show that for any delta, if I integrate over a region that is not around the origin, that the Fejer kernels will tend to 0, right? So I claim now, claim, this is the most important one, claim, let delta be greater than 0. And what can I say about this? The limit, as n approaches infinity, of 1 over 2 pi, well, I can throw that away, we don't really need that. Just if I integrate over delta less than x less than pi of this Fejer kernel, Kn of x dx and absolute value. Again, I don't need absolute value since it's not negative. I want to show that this limit goes to 0 over here, right? Well, what can I say? I can say that this is greater than or equal to 0. This limit is clearly greater than or equal to 0 by the non-negativity. This is greater than or equal to 0. And this limit is less than or equal to the limit as delta as n goes to infinity of, I'll pull that 1 over n plus 1 out, n plus 1. Then if I integrate over delta, all the range of the range that is bigger than delta, right? Delta less than x less than pi. Now, what will I have over here? I'm going to replace this. I can bound this, make this thing is no more than 1. So this is 1 over just the sine squared of x over 2 dx. And of course, in this range, the absolute largest this thing can be over here is the sine, of course, is going to be 1 at pi over 2. I can make this denominator larger by making the value smaller. So in other words, this is no more than, this is less than or equal to the limit as n goes to infinity of just a 1 over n plus 1. And then whatever, a constant, of course. I need another constant over here just for the length of this interval. It depends on delta. It's sort of irrelevant, like pi minus delta, obviously. And then the sine squared of just delta over 2. Of course, delta is just a fixed constant over here. So as n goes to infinity, this limit goes to 0. So in other words, what we've just shown this Fejer kernel is an approximation to the identity. So hence, Kn, this family, n goes from 1 to infinity or 0 to infinity, is an approximation to identity. That's beautiful, because what do we know about approximations to identity? I know, therefore, so hence here's our proposition, prop. If f is continuous on negative pi to pi and 2 pi periodic, Okay, so I have a continuous 2 pi periodic function. I know that Kn convolution f converges uniformly to this function f. Converges uniformly to the function f. Okay, that's because it's an approximation identity. In other words, what we can say over here is we can say, and what we call these things sometimes, these are sometimes written as sigma n of f, and these are called the fair means. So these are called the fair means of the function. The fair averages are these of x, right? Uniformly. Great. So these fair means converge uniformly, and these are trigonometric polynomials, right? So in other words, I know that trigonometric polynomials are dense, right? So in other words, hence, trigonometric polynomials are dense. Are dense in the space of continuous functions. On negative pi to pi. Excellent. Now what this allows me to do is this allows me to prove the Parseval theorem, because if we recall from a previous video, what do we know? We know that if I can uniformly approximate these things, so we recall that Sn, if Sn are the partial sums, so if Sn are the nth Fourier partial sums, then I know that Sn of f minus f in the L2 norm is the smallest, right? It's the best approximation in the mean with respect to the inner product, right? So this is going to be smaller than these fair means of the function, right? In L2. But of course, that's controlled by the L infinity norm, right? So this is tending to 0 as n goes to infinity, right? And so now I can use this together to conclude the Parseval theorem, right? Because we recall that we know that Sn of f minus f squared plus the sum of the square of the nth Fourier coefficients in L2, j less than or equal to n f hat j squared, is just equal to f in L2 squared. Now, of course, as n goes to infinity for a continuous function, if we assume that this function f is continuous on the entire unit circle, then these numbers have to tend to 0, and so we're able to conclude the Parseval relationship. And so it's the Parseval theorem. So Parseval theorem says that the what? Says that the L2 norm, that if I sum up the squares of the Fourier coefficients, j and z, f hat of j squared, that has to be equal to the L2 norm of the function squared. Of course, what's the L2 norm of the function squared? The L2 norm of the function squared is if I just have this formula over here and put a squared over there, right? So the L2 norm squared is just going to be that expression. So in other words, this L2 norm squared over here, L2 norm is just 1 over 2 pi, the integral from negative pi to pi of the function f of x squared dx. So in other words, if I sum the square of the Fourier coefficients, the sum of the square of the Fourier coefficients is equal to the L2 norm of the function squared, and that's the Parseval theorem. We can polarize this to get other versions of the Parseval theorem as well, but this is the main ingredient. This allows us to compute a large class of infinite sums by using the Parseval theorem. Thank you very much.